Now that we have both versions of the fundamental theorem, it's easy to understand what to do in a problem like this. Here we have a function that's defined by an integral, but instead of having just the plain variable up here, we actually have a function of the independent variable. But if f is continuous, then we know by part one of the fundamental theorem that little f has an antiderivative. Let's call it capital F, in which case we're really talking about taking the derivative of that antiderivative evaluated at these two endpoints. So little f has an antiderivative, we'll call it capital F. We'll plug in the upper bound, which is g of x, and then we'll plug in the lower bound. So this integral, we can find that. We know it has an antiderivative, and then we know by part two of the fundamental theorem that we can evaluate this definite integral by finding the antiderivative at the two endpoints, and then we just find the difference. So use both parts of the fundamental theorem here to do this. Now we're going to take the derivative of that. Now the derivative of this, since that's a constant, it doesn't depend on x, that derivative will be 0. But the derivative of the first part, we'd have to take the derivative of the outside, and then we'd have to evaluate it at the inside and multiply by the derivative of the inside. However, capital F is purposely an antiderivative of little f, and so the derivative of capital F is little f. So we get little f at g of x times g prime of x. So we've already seen this result. If you need to take the derivative with respect to x of the integral from a constant up to a variable of some function of a dummy variable, d-dummy variable, you just get f of x. What this is telling us is that if you have to take the derivative with respect to x of the integral from some constant up to an actual function, then what will happen is just like before, this bound comes down and lands in there and the integral disappears. But you have to multiply by the derivative of that function that was up in the bound. Here's an example. We're going to take the derivative with respect to x of the integral from 0 up to x squared of sine of t squared dt. Now, according to this pattern, if you take the derivative with respect to x of the integral from a constant up to a function of some function of a variable d variable, then what you get is the function in the bound comes and lands inside the function you were integrating, and then you multiply by the derivative of that function in the bound. So in this case, we have sine of t squared. Well, that x squared is going to land in the place of t, so we'll have x squared, and then it's t squared, so that'll be another square on that. Then we have to multiply by the derivative of this function up in the bound. Our function in the bound is just x squared, so we multiply by its derivative, which is 2x. So altogether we have a 2x times the sine of x squared squared would be x to the fourth. One more example here. Here we have a function, but it's an integral function and it's raised to a power. So according to the chain rule, the power would come down, and then we'd have our function of x to 1 power less. Just copying down that function takes a second. So the power reduces down to 4. Then we need to multiply by the derivative of that inside function. And of course the derivative of that inside function fits the pattern that we were just discussing. So let me recopy what we have so far. Now we'll take the derivative of this. Our rule is that the function will come down and land in here in place of whatever the variable of integration is. Then we'll multiply by the derivative of that function, which happens to be cosine x. So we'll get 1 plus sine of x cubed would be sine cubed of x. That all to the 7th. Now we have to multiply that by the derivative of sine x, which is cosine x. Now we could actually go further with this problem. We could expand this, but by the binomial theorem, if we expand this, since it's to the 7th power, there are going to be 8 terms. Now each of them is going to be t cubed raised to some power, so we'd have to integrate these 8 terms and then evaluate them between the endpoints. I don't think that's really the point of this example, to figure out what that integral is, just to be able to take the derivative of some function that's defined as an integral, where instead of having just x in the bound, you have some function. So I think we'll go ahead and stop there even though we know it is possible to complete this integral calculation. Let's go ahead and leave it like it was given to us. So undone. Now let's see, we have a problem that we need to solve, a differential equation. Now dy dx is going to be the square root of 1 plus x squared. So this is a very simple problem. If you think about it in terms of separable equations, there's a function of, the function of y is just a constant, so it's easy. I'm just going to integrate both sides with respect to x here. Okay, now looking at that, the integral is dy dx times dx. That's the definition of dy, and if you integrate dy, you get y. And then here, I need to find an antiderivative of this. Now, we can actually find an antiderivative. There are techniques for doing it, but we don't at this point recognize what that antiderivative might be. And so, since we don't recognize what the antiderivative will be, we could use the fundamental theorem. The fundamental theorem says that every function that's continuous, and this one is certainly continuous everywhere, has an antiderivative, and you can build that antiderivative as an integral function. So I need some constant to start off, and I know they tell us that this function applies when x equals 1, so I'm going to start at 1 because I need a starting place. So I'm going to integrate from 1 up to x the square root of 1 plus t squared dt. That I know is an antiderivative by part 1 of the fundamental theorem, so I found an antiderivative of this function. Okay, now there could be, that's one antiderivative, there could be an arbitrary constant in there. Now my next step is to determine, well, what is the arbitrary constant? So if you look at what we have so far, we have the y as a function of x, but we need to know this constant in order to completely determine y. But they tell us when you plug in 1 for x that you're supposed to get negative 2. On the other hand, if we plug in 1 for x, we have the integral from 1 to 1 of the square root of 1 plus t squared dt plus c. This is an integral over a 0 width interval, and therefore that integral is 0, and now we know that our constant is negative 2. So we can specify y completely now as a function of x. It's the integral from 1 to x of the square root of 1 plus x squared, oops, I need to use a dummy variable there, 1 plus t squared dt, and then c is minus 2. I made a mess of that, but the reason we need to use a different variable here, if you notice what you would do, once we know how to find an antiderivative of this, we'd find an antiderivative, that would depend on the variable of integration, but then the variable of integration gets replaced by the two bounds. And so for this to turn out to be a function of x, we don't want to have x here because that would be replaced. We'll have some other variable. Notice the name of that variable doesn't really matter as long as it's not the variable that's up here in the bound. So let me recopy my solution since it's so messy. We have y of x is the integral from 1 to x of the square root of 1 plus t squared dt. Take that whole thing and subtract 2.